Today we will talk about the famous von Neumann model. And after this class, I will post the first homework. I think if you submit your homework on time, you should be fine. I fully understand that some of you may not be in E or CS, so I will be easy on the homework. So the first machine, computer is actually created ENIAC. I think it's used to compute some cryptographic task. And then they try to integrate more programs into the computer, so they need a larger memory space. And then eventually we have the von Neumann architecture. So the basic structure of the von Neumann architecture or von Neumann machine is that you have a memory which can help you to store the data and instructions. You also have a processing unit. Potentially, it can perform arithmetic, logic, and even analog computation. And then you also have a control unit for you to decoding the instruction. So this is the so-called von Neumann architecture. Now, yes. So the major part of this architecture is the processing unit. Typically, it's your CPU, and then you have the memory. Typically, it's the memory DRAM. You have input, disk, keyboard, scanner, and then you have a monitor, LED, and a disk. Disk is not a part of the memory. Disk is actually your I/O input and output, and all the transition happen between these components that is controlled by the control unit. Although in this class we talk about this architecture, nowadays more frequently you should hear about non-von Neumann architecture, because people realize that potentially this part could be a bottleneck. So the memory, the interconnection between memory and the processing unit is a potential bottleneck, particularly for the big data application, graph application, deep learning application. So people actually create a lot of non-von Neumann architecture. I think the most famous one is the so-called processing in memory. They just integrate these computing units into the memory so that you don't have this interconnection anymore. This sounds like it's very, sounds like that it's very easy to implement such so-called processing in memory concept. But unfortunately, it's not. Why? Because nowadays when you try to buy some CPU on the market, it may fabricated by 8 nanometers, so the latest process technology. However, for memory, people try to use some very old process technology like 16 nanometer or 30 or even 60. Why? Because for the memory part, you can consider that now everyone, even your laptop, has 16 gigabyte. 16 gigabyte is a 16G multiplied 8. You need to fabricate many cells. Any of these cells failed, the memory chip failed. So that they are very sensitive to the cost. That's the reason why they prefer some mature, very well-known process technology to guarantee the yield, the cost. That's because these two components, the complicated process technology, it's very difficult to integrate them together. And the CPU part or the processing unit part, processing unit, everything, architecture, devices, transistor in this part are highly optimized for the performance. Now your CPU can run at a 3.8 or 4 gigahertz. For this part, the power is not first priority. However, this is not the case for the memory. Here, the transistors are highly optimized for the leakage, for the power. The performance is not the first priority. The memory, the memory does not have to be, does not have to run at maybe 4 gigabyte. No, 4 gigahertz. No, it's much slower. So the transistor for these two parts needs to be highly optimized for different jobs. That's another reason why you cannot make them together. So although people actually hate this architecture, but this architecture actually is still dominating all the computing system. So this is a overview of the memory space. This is a one array. We may have MB in each entry, and totally we have a total K entries, and each entry can be identified by a K bit address, and each entry can help you to solve MBs here. And then you can issue load and store to read some data from a location of this array and store some data to some particular specific location here. The CPU, the processing unit, and now let's talk to the memory because you may use different types of DRAM. For example, some of you may use DDR. Some of you may say different DDR interface may have different protocol, different devices. Typically, the memory controller is in charge of talking to the memory, the real memory. That's the reason why if you want to have DDR5, you have to buy some particular generation of the CPU, because only that type of CPU contain the memory controller, which can talk to the DDR5 DRAM. But the major part of the memory interface is the memory address register and the memory data register. When you try to read some data from location 1, you just write the address to the address register. And then issue a read signal. And then the neuron will write the data to here. When the data is ready, the memory controller can fetch the data and return the data to the CPU. When you try to store some data, you write the data into the data register and write the address, the target address to the address register, and then memory controller issue a write enable signal. Then this piece of data will be written into the DRAM space. And then we will talk about the percentage unit between the CPU. Typically, the CPU can support arithmetic and logic operation. So they use an ALU. And you may have many other function units, like MAC, multiply, accumulation, square root, specialized function unit. The LC3 here is a instruction set we will talk about in this lecture. It's short for little computer. It's actually a simplified instruction set. So for this simplified instruction set, it can confirm. And then in the CPU, we also have some registers, which can help you temporarily store some data. You can store the operands and the results of ALU and the function units to the register file. So the LC3, each of them is a 16-bit. And then we will talk about word size. Most of the modern is 64 bit. For example, 86. Even your mobile phone ARM core are actually 64 bit. 64 bit means each operand of your ALU can be 64 bit. You can do a 64 bit addition. You can do a 64 bit number multiply another 64 bit number. To support these operations, you need a 64 bit register. You need a 64 bit memory path, so that each time you can read a 64 bit data. But in this lecture, the LC3 is only 15 bit, because it's a simplified instruction set. And then we will talk about the I/O. Nowadays, the I/O becomes more and more important because your data is so large that your memory cannot contain all the data. Then the I/O can be summarized as the devices for getting data into and out of the computer memory, including your disk. Maybe sometimes even your GPU is an I/O device. Output can be also a disk. So each device has its own interface. Typically, it's a set of register like the memory address. So LC3 supports the keyboard and the monitor. There's no disk. Keyboard has data register and data register. And the monitor also have a data register and status register. Some devices provide both input and output, like your network, wireless network and wired network, and your disk. So the program that control the access to one device is usually if you just plug your network card into your computer, it may not be recognized by your operating system. Sometimes you need to install a driver to enable the access to the device. At last, we have a control unit. The control unit can schedule all the execution of the program. The major two parts of that is the program and the instruction register. So the instruction register for the current instruction, which is executing in the CPU. The PC contains the address. So the program counter actually store the address of the next instruction. The next instruction may not be the neighboring instruction. It can be a totally different instruction. Because you have if-else loop, right? You may not be able to always sequentially execute your code. So the major job of a control unit can be summarized as: first, it reads one each instruction address on the PC, because the PC specifies the next instruction, and then it decodes the general sequence of all the other things. A instruction may take several machine cycles to complete. That's so-called pipeline. So each cycle, the controller may really require signal for another instruction. So this is the summary of the instruction processing. So basically, there are 6 steps or stages. The first one is an instruction fetch, instruction decoding, evaluating addresses, and the fetch the operand from to do the job, execute the operation, and store the result. I believe this is the instruction processing steps in LC3. The instruction is a fundamental unit of work. It can describe 2 things. The first one is opcode. Opcode indicates whether you do addition or multiplication. It's the type of operation you need to perform. The other one is operands. So it's the data or location to be used for that operation. An instruction is actually encoded as a sequence of bits. Sequence of 1, 0. It's the same as your data. Typically, the instruction has a fixed length. Particularly, this is particularly true for the read. Reduce the instruction set architecture. Why they need a fixed length? Because they need to, it's easy for them to decode all the instructions if your instruction has a fixed length. Otherwise, they need to do a lot of if-else. If your instruction has 8 bits or 16 bits or 32 bits, what will happen next? Then such if-else will significantly reduce the frequency of your CPU. And then the control unit will decode the instruction, generate a lot of control signals to perform the operation. The operation is either executed completely or not at all. If your operation is not executed, why? Because you are in the unselected branch of a if else. So in that case, the CPU does not have to run operation. Otherwise, it will be completely executed. So these are formats, the instruction formats, all the instructions, so-called instruction set architecture. This is the most important for a CPU. No matter how your CPU is fabricated, your CPU needs to implement one of the instructions. For example, the x86 or ARM instruction set. Because even for the ARM instruction set is very complicated, and it also has a 64 bit. So we will use the LC3. So this is the addition instruction for LC3. The LC3 instruction set is a 16 bit. So you can see. And the opcode of add here is actually 3 zeros and 1. When the control unit see this, it will know, okay, this is the addition. And this is so-called opcode. The opcode is 4 bit. So it has 3 registers. I'm sorry, it has 8 registers. 8 registers. So in order to index these 8 registers, how many bits they need? 3, because this is the 8. For the addition, you need to add 2 numbers and generate a sum. So that's the reason why you have source 1, source 2, and destination. These 3 are registers, and each of them is a 3 bit because totally you have 8 registers. And you can assign any number here so that you can use all the registers. And they will constantly set these 3 bits to zeros for the add instruction. So the meaning of this add instruction is that add the contents of R2. This is the R2, okay, because you can convert this binary number to decimal. To the contents of R6. This is R6. and store the result, store the sum to RC. This is also RC. Although in this example, the source 2 and the destination are the same, because they have two fields for you to specify. They can be different. And then the first step to process instruction is that you load the next instruction, which will be executed immediately. And the result, the address of that particular instruction is actually stored in the PC program counter into the instruction register, which is the IR. You copy the content from PC to MAR. MAR is the memory address register. You want to read the content in the PC. So that's the reason why you do this. And then if you read signal, and then after the memory gives you the data, you copy the data from the memory data register to the instruction register. So basically, these three steps describe how can you achieve this goal. And then the control unit increase the PC may not necessarily by one, because sometimes you have a if else control branch. But in most cases, you increase this value by one. This is what the CPU will do in the fetch state. And then the control unit will do the decoding. The first step of the decoding is you identify the opcode, like in the add instruction, it's a 0001. When you meet 0001, you know that, okay, this is the addition. So typically they use a decoder to achieve that goal. Depend on the operands. Opcode, you can actually identify the operand from the remaining bits, like 3 register, source 1, source 2, and destination register. When you have all the register names, for example, in that particular add example, you have R2, R6, R6. Then you need to evaluate whether you need to read this data. You will not. For that particular instruction, yes, of course you need to do that. And then you actually do the read operation. You load the data from read. Data is running. Now you have all the data you need. And then you need to do the real addition. So think about it. In order to perform an addition, you need to do all these. Only the fifth step actually do the addition. So eventually you can write the addition result to R6. This is how you do the right operation. you still need to write these prefix to memory addresses, right? And data to the memory data address, and E to the write enable signal. In most cases, the PC counter will be increased by 1. If you have a loop or branch, you need to figure out how to jump to another instruction, which is not neighboring instruction of the instruction stored current instruction. So you need actually some special instruction to achieve this goal. And these instructions are so-called control instructions, like the jump and branching. This one is unconditional. You can directly jump to some instruction address. But for this one, they will first evaluate some condition. Only when the condition is true, you do the jump operation. Again, the jump instruction also has and the opcode of jump 1100. And then for these 3 bits, they specify the base. What does the base mean? The base means base actually store the address of your instruction you want to jump to. For example, the meaning of this instruction is that load the contents of R3. This is R3. R3 is the base into the PC. So that next cycle you will execute the content stored in R3. Because the program counter always store the instruction you will run in the next cycle. Again, eventually the data will be stored like this. So you can see that here we only have 1 and 0, nothing else. So the instruction looks like data, 1 and 0s. And you have 3 different types of instructions. The first one is a computational instruction, addition, multiplication, logic operation. The second one is a data movement instruction, load, store. And the last one is a jump, some control instructions. And you will process the instruction in this order. Instruction set, instruction decode, address evaluation. So you need a memory operation. Prepare the outputs and real execution, and then store it back to the memory. So each instruction, even for you jump, for you load, go through all the stages. So this is the control unit. The control unit itself is actually a finite state machine. So here is the simplified diagram of the LT3. I will widen you the speed diagram in some appendix. I will post that on Canvas. So basically, each box here is one step the control unit has to do. Only after the control unit understand this instruction, the control flow will go through different branch here. For example, if your instruction is reaching, you need to go these many stage. If your instruction is done, you need to go through these. But all the instruction will go through at least 4. Only after these 4, the control unit can understand what does this instruction mean. So the control unit will repeat the instruction processing sequence as long as the clock is running. If not processing instructions from your application, and then it will process the instruction from the operating system, which means you have a context switching. The CPU will need to respond to the operating system, and then maybe you turn back to your application or maybe switch to another application. So the operating system itself is a specialized application program, which should have the highest priority in some cases. So to stop the computer, you can actually set the clock generation signal with 0. How can you do that? You just add this is a 0. Everything and a 0 will be a 0. When control unit stops seeing the clock signal, it can also stop. Any question? If no question, I will stop today. So in our next class, I will present the detail on the LC3 instruction set. I will also, today I will post the homework 1. Don't worry, it only includes 4 sub-problems. It will be due in 2 weeks. Okay. If you have any question, please email me. Thank you very much.